Okay, something's up. Okay, guys. So, no, no compass needed. I don't know what happened to. Oh. All right. All right. So let's talk about 1-4 today. We're covering the whole section, which is inductive reasoning. So, your I can statement is you can use inductive reasoning to make conjectures about mathematical relationships. 3 new vocabulary words are conjecture, counterexample, and inductive reasoning. Okay. We're going to move straight into the essential questions. So I want you on page 14 in your companions, please. How is inductive reasoning used to recognize mathematical relationships? Okay, so a lot of this stuff today is going to be well done. Okay, but think of it this way. We are starting to get kind of the building blocks of proof writing. Inductive reasoning, identifying patterns, is part of proof writing. Okay, so we need to make sure that we can walk before we run. Does that make sense? So if we take a look at this, the definition of inductive reasoning, it is a type of reasoning that reaches conclusions based on a pattern of specific examples or past events. How can you use inductive reasoning to determine what appears to be the next two terms in each sequence? So if we look at this first one, we have 88, 82, 76, 70, 64. There's a consistent pattern, almost like a common difference. You guys remember that from algebra? Common difference, right? Of subtracting 6 each time. So the next two terms would be 64 minus 6, which gives us 58, and then 58 minus 6 giving us 52. Now, here's the thing you need to be aware of with this stuff. My God, I can't win today with this thing. It's not always going to be a common difference. There'll be a pattern, but it's not always going to be a pattern with a common difference or a common ratio, okay? And that's what this next example shows. So if you look here, we have 3, 5, 9, 15, 23, right? Look for a pattern, observe the terms, increase by successive multiples of 2. So in this case, if we look, we have 3 added to 2 gives us 5. We add 5, adding additional 2 here gives us 9, adding additional 2 here, 6, which gives us 15, adding 8, 23, adding 10, 33, adding 12, 45. If we wanted to find 3 terms after, we would add 14, 16, then 18. Does that kind of make sense where that's coming from? So this is just to get you an idea of patterns exist that aren't necessarily just having a common difference or a common ratio. Okay. So what I want you guys to do is I want you guys to try it 1. You have A and B. I'm going to give you 3 minutes. For B might take a minute, and that's okay. Talk with people about it, okay? And see if you can identify that pattern.
Then I can't help it. Calculator's going to be the way to get that one.
Okay. Here's a tip, pro tip, guys. I know you guys really love decimals. I get it. Decimals can be fun. Decimals give us money. It's kind of cool, right? If it starts in fractions, it's got to end in fractions. Okay. So remember some of your converting from converting decimals to fractions from maybe algebra? Yes? Remember that calculator does that? Refresh yourself on that skill. If it starts in decimals, it can end in decimals. If it starts in radicals, it should probably end in radicals. We're gonna get there. Okay, so just FYI. This class is very big on exact solutions and approximate solutions. A fraction is considered an exact solution. Okay, so just keep that in mind. So I want the next two fractions here. How are we doing? Still figuring it out? Whatever you'd like to do. That's why I offered it. But just know that like if you take it during class, you just need to find a conducive day where you're not going to be up all night with your work. Today might be one of the days that you're not trying to take. All right, let's talk about this. So I think letter A we all got, right? What was the rule for letter A? What was happening here? Good. Dividing by 2, yep. All right, so everything's divided by 2, which means the next two terms here ended up being what? Good. 50 and 20. I'm sorry? Very good. So we're going to have 50 and 25. All right, who can tell me B? Does anybody know it? Go ahead. 1 1/3. Okay. How would we do that as an improper fraction? 4/3. Don't be afraid of improper fractions. They're a lot easier to work with than mixed numbers, but you were correct, sir. Okay. So in this case, we are multiplying by each by 4/3. So what's those next two terms? Go ahead. What'd you say the first one?
Or 512 nines.
Okay, that's okay.
That's what I wrote.
Okay, over 9. And then what's the second one?
2048.
Very good. Just out of curiosity, because I'm trying to get a visual here. I know a lot of you are freshmen. How many of you, your teachers, like just harped mixed numbers the whole time? No? Okay. Get comfy with impropers, especially if you're going to be taking calculus your senior year. Trust me, improper fractions are your friend for that. Okay. Algebra 2, same thing. So it's okay to have improper fractions here. All right. Well, I'll just be the Mad Hatter. You guys ever see the hat? It's like 10/3 improper. Yeah. Just there you go. Mrs. Smith loved movies. That's what I do. All right. Anyway, example 2. So what we did with the last part was inductive reasoning. We identified the pattern, which, oops, I forgot to mention. Let's go back just one little thing. Okay. This and this, identifying that pattern and kind of writing in it words, those are known as conjectures. Okay, those are like your rules. Okay, and then you need to kind of show if it works or doesn't work. All right. So now what we're going to do is we're going to talk more about conjectures in the next slide. So it says a conjecture is an unproven statement or rule that is based on inductive reasoning. What conjecture can be made about the number of dots in the nth term of this geometric pattern? So if we take a look, right here are our term numbers. This is term 1, term 2, term 3, term 4. We saw that in algebra, yes? Okay. And then we have just the number of dots. These are like the end results. We have 2 dots for term 1, 6 for term 2, 12 for term 3, and 20 for term 4. So the pattern that seems to be happening here is the number of columns is one more than the term number, which makes sense. 1 plus 1 gives us 2, 2 plus 1 gives us 3, and so on. The number of rows is the same as the term number. So if you look, there's 4, 4, 3, 3, 2, 2, 1, 1. Okay? So if we wanted to express this algebraically in order to get that conjecture or that rule, we can kind of just look at this again saying, okay, rows is just the term number, and the columns is the term number plus 1. And when we set this up, we're going to have, not that, go away, thank you. We're going to have n times n plus 1, and then we distribute, which gives us n squared plus n. And this right here will be the conjecture for the number of dots. Does that make sense? We're going to do the example in your book together so that this way you guys understand what's going on, because it's a little different. So let's take a look at the example and try it. They want two things. First, how many dots are in the 5th and 6th terms of the pattern? And then part B, what conjecture can you make about the number of dots in the nth term of the pattern? Okay, so first things first, let's take a look at number 2. Or 2A, sorry. So this is going 1, 2, here's term 3, here's term 4. If we count, we see that this has 1, this has 5, this has 11, this has 19. What's the 5th term and the 6th term going to be? Who can tell me? Go ahead.
29 and 41.
Very good. 29, 41. Does everybody see why that is? Who doesn't? So it's basically saying we're going to have 5 times 5, because if you look, we have the square here. That's 16 plus an additional 3, giving us 19. So this will be 5 times 5, it gives us 25. And then we're going to have plus an additional 4, because these top parts are going up by 1 each time, or the term number minus 1. Same thing with 41. That'll be 6 times 6, which gives us 36, plus the additional 5. Does that make sense where that's coming from? Okay, now how are we going to represent this algebraically? So what's happening here is if I wanted to highlight some stuff, I see that I have, can you guys see that yellow? That's a little light, isn't it? It's too green. I see I have kind of this square, which is 2 times 2. I also have this square, 3 times 3. I also have this square, 4 times 4. So if I were to just create a square, I know that I'm going to have n times n to get that first part, right? How do we get the last part? Those little dots above it. Who's got an idea? Go ahead.
I think
It's n minus 1, yeah. So the dots above, here we have 1, we have 2, we have 3. It's always that number, that term n minus 1. Now, how are we going to set this and this up? What goes between these two? Like, what physical operation do we do after we found this square with these dots? Good. We added them. So this is going to be n times n plus n minus 1. N times n is what? N squared. So we n squared plus n minus 1. And here's our number of dots. So here's our conjecture. How we doing? Questions, comments, or concerns? All right, let's take a look at the next example. We're not going to do example 3, but I did like the triad activity, so we're going to look at that. Based on the data about how many members would you expect the chess club to have in its 5th year? So here's the data. What's the pattern? What's that conjecture? I want you guys to find the conjecture and your 5th term. Give you like a minute. Shouldn't take too much. Shouldn't take too long. All right, who can tell me what is the conjecture? Go ahead.
I said each year one more person is added to the people that join. So like the first year 3 people joined, then 4, then 5.
So it's the term number plus how many? 1. So we're adding n plus 1 to each year. So there's our conjecture. What about that 5th term? How many are we going to have? Go ahead. 28. Perfect. Questions on that? Okay. Let's move on to example 4. Anybody still writing this down? Okay. Okay, so now we're going to talk about a counterexample. So we just learned 2 things already. We learned inductive reasoning, which is identifying the pattern and continuing on with it, right? That's problem solving, figure it that way, or pattern recognition. We learned what a conjecture is. That's the rule. Now, we can't prove conjecture is true unless we can prove it for everything. And there's no way we're ever going to be able to prove it for everything. Okay? Even with the algebra, we can't like go through every number because numbers are infinite, right? So it's never going to happen. But we can prove conjectures false. And we do that by using something called a counterexample. All right? Now the definition's right there. It says a counterexample is an example that shows a statement or a conjecture to be false. It just proves it false completely. Okay? So the conjecture they're giving me is a polygon has 2 fewer diagonals as sides. Now, if we started with the square, that would be true, right? A square has 4 sides. We have 2 diagonals. However, as soon as we get to the pentagon, you can see that we actually have an equal number of sides and diagonals. So therefore, this conjecture is false because this is our counterexample. Does that make sense? You only need 1 to prove that it doesn't work. So let's do an easy example. The color orange is the only color that's also a fruit. Can you prove that conjecture wrong? And if so, what would it be? Give me a counter. Nobody had the big box of 64 crayons?
Are we just saying like in general, like a color, or can you just?
Is there any other colors out there that are also a fruit?
I don't know any of them, but there's probably a version of a type of color that would be the same name as the fruit.
Okay, but you need a specific example.
Peach, there's peach crayon.
There's a peach crayon, right?
Peach crayon means there's peach color. There's peach color.
Yeah, so there's my counter, right? I think green apple is another one too, isn't it? Isn't there a green apple crayon?
No. Well, yeah, there probably is.
So yeah, if you can provide that counter example, it works. Okay, if you can't, different story. All right, sound good? Questions? All right. All right, let's take a look at number 4. So it says, what is a counterexample that shows the statement, the sum of two composite numbers must be a composite number? And we're trying to prove it false. So here's a hint. If you don't remember what a composite number is, a number that is divisible by a number apart from 1 and the number itself. So which means a prime number is only divisible by 1 in itself. A composite number, like an example 6. 6 is divisible by 1 itself and then 2 and 3. That's composite. However, 3 is prime because it's only divisible by 1 in itself. Okay? So give me a counterexample that proves this false. We have to add two composites. Basically, we need to add two composite numbers together and get a prime number. So what two composite numbers add together can give me a prime? I'm sorry? 21 and 8. That gives us 29. Is 29 prime? Yeah. We could do this all day, right? But did we just prove the conjecture false? Yeah, we only need one. She used 20. I used 4 and 9. Give me 13. Each one of you could have something different, and it's okay. You just need to prove it wrong, right? All right, so that's how we know that conjecture is false. And this happy fellow right here is our counter example. Questions on that? All right. Example 5, for each conjecture, test the conjecture with several more examples or find a counterexample to disprove the conjecture. A polygon with 4 congruent sides is a square. What is that happy shape called? What is it? What's it called? Yeah, what's it called? It's a rhombus. Rhombus has 4 congruent sides, yes? Hi, glad you're back. If it has 4 congruent sides, did we just prove the conjecture false? Yeah, that's all it takes. So nice, so simple, so easy, right? Let's take a look at this next one. If a figure is a convex quadrilateral, then at least one angle is greater than or equal to 90. Here's the deal with this one. First off, how many of you know what convex means? Okay, so convex means that there's no like caving inward of the shape. If I drew something like this, that would be an example of concave. Still a polygon because it connects, but it's a concave polygon. Convex polygons kind of everything's outward. Okay. But if we take a look at this, here's an example of a trapezoid. The figure has two obtuse angles right here and right here. This is a square. It has 90-degree angles. It said greater than or equal to 90. It's working. And it says at least one, not at most one. This one says the figure has one obtuse angle. So far, all the examples we have are working out, right? Yes? Do we want to continue this for every dang polygon that exists? No. So for now, we can assume it's true, but we can't prove it's true. Does that make sense? Do you guys understand that difference? Okay. So just be careful with something like that. So it even says right here, none of the figures are a counterexample to the conjecture. However, just because a counterexample cannot be found, you cannot conclude that the conjecture is true. All right. All right, let's take a look at number 5. Try it 5. Test the conjecture. It says for each conjecture, test the conjecture with several more examples or find a counterexample. Letter A. It says for every integer n, the value of n squared is positive. What do you guys think? Is this true? Can we assume it's true? Give me some examples. -6 squared. -6 times -6 gives me 36. If I want the positive side, 6 times 6 gives me 36 as well, right? Okay. Something's irking me though. And this is where we have to really fine tune our skills a little bit to include as much as we can. What's 0 times 0? 0. Is that positive? It's not, right? Is 0 positive or negative? No. So there's my counterexample. This doesn't work for everything. Okay. You guys, that's the 6, -6 and the +6, totally valid argument. But there is, in fact, a counterexample. So just make sure you look at everything. Okay. All right. A number is divisible by 4 if the last 2 digits are divisible by 4. Someone give me a number where the last 2 digits are divisible by 4. So we're talking like 08, 16, right? Numbers like that. Give me a number. You don't need to reinvent the wheel with this, I promise. All right, here's one. Is that divisible by 4? Yeah. If I divide it by 4, what do I get? Good. 754. Very good. Anybody got another number? So far, I didn't find my counterexample. Anybody got another number? I did this like 5 different times. I'll be honest. I did 5108. I did 7712. I did 11328. I also did 116, just to kind of see if it works smaller. Every one of these numbers was divisible by 12. Yeah, or by 4, I mean. Sorry. Yeah. But can we do it for every possible example? No. So we can assume it's true. Yeah. So we're going to say assume true. And that's only because we couldn't find that counter. Questions on this so far? All right. Habits of mind. I want you guys to take a peek at that. It says Tyler says that only one example is needed to prove that a conjecture is true. Do you agree? Take a minute and write down what you think. All right, who's still writing down about Tyler? All right, first up, Tyler, is he correct? Thumbs up or thumbs down? Good, I like it. Why is he incorrect? Anybody? Go ahead.
Because everything that he's testing has to follow the rules of that conjunction to be true. So checking one wouldn't work. He has to check everything.
He has to check everything to prove it's true. Okay, any other theories? Go ahead.
The one thing that he's testing as an example could be the exception and not like the whole. It could be the one thing that's different from all the others.
It could be that counter example. Good. Okay. Same thing.
You can never prove something true unless you test every single possible possibility.
Okay. Yeah. So we have a lot of really good examples as to why Tyler is wrong. Poor Tyler. He didn't pay attention. You guys did. Proud of you. Okay. So again, you have to test every possible theory. That Tyler's not going to do that. And testing just one isn't going to work. It could be the counter example, right? There's so much that Tyler is missing. We can assume it's true. We can never physically actually prove it's true though. Okay? Makes sense. Any questions? Homework is on Savis. Get going on that. I think it's 8 problems total. And those of you watching at home, have a great day.